Thank you very much for staying with us for such a long time. Thank you to all the participants of this meeting. I think it's been really very exciting. And in my talk, I would like to return to how I started this meeting by asking what's special about humans. And I would like to argue that what's special about humans is not just communicative language, as we've been mostly discussing today, but perhaps similar to what discussed at the beginning of this afternoon, a deeper notion of language, a language of thought that allows us, even without words, to make sense of the world. And I would like to argue that humans are extremely special in this respect, even when it comes to super simple stimuli, like spatial sequences or sequences of sounds. And I would like to show you empirical evidence for that. Some of this argument has been made in this recent book, How We Learn. Of course, it's a bit more general than that, but I talk a little bit about the comparison of brains with artificial neural networks. And I would like to argue, I have argued in this book, that neural networks have been excellent in helping us understand how synaptic changes could lead to sophisticated learning, especially when there are millions or even billions of synapses that can change. They've been excellent at capturing the early stages of vision, and they have been, as we saw in Christoph's talk, they are beginning to be pretty good at capturing aspects of language processing, and especially how it occurs at the brain level, purely as a regressor. But in this domain, I will argue that there are still many domains in which the human brain keeps the upper hand. First of all, we've discussed the learning from a small number of examples, sometimes a single trial, and I would like to argue that this is due to Bayesian-style reasoning, so much more efficient reasoning than gradient descent. But today I will focus mostly on the second aspect, which is that humans learn recursive or compositional representations, and they do so in a broad variety of domains. So maybe we should say that there are multiple languages in the plural in the human brain. This allows us to discover compact, abstract, symbolic representations of knowledge, and that must have been a huge advantage in evolution. And one thing I will not talk about today, but which is discussed in the book, is that learning becomes explicit. Unlike the distribution of knowledge in weights, in millions of weights where knowledge is hidden, knowledge at this level is explicit, can be shared with others, and we benefited as a human species a lot by this aspect of social cooperation, which is still not at all modeled in machine learning at this point, but could be very interesting. So I will talk mostly about this central part, the learning of recursive representations, and I would like to argue that, in fact, virtually all of the aspects in which humans are special, such as music, language, mathematics, are based on such a combinatorial ability. So the basic hypothesis is that humans are characterized by their capacity to combine discrete symbols into nested structures, and that this is specifically human, that it allows us, and especially children, to create new mathematical concepts by recombining existing ones into novel expressions. So I will try to show you that our concept of quadrilateral is a little formula in the head, which says four-sided figures, and that squares are constructions on such formulas. The idea, of course, is very close to what was defended by Hauser, Chomsky, and Fitch, the idea that there is a recursive operation, which is the basic, perhaps the single difference at the core of the human language faculty. But the idea is even closer to a later paper by Tecumseh Fitch, which he calls the dendrophilia hypothesis. It's not the hugging of trees, this is a joke, but it's really the idea that the human mind finds hierarchical and builds hierarchical structures all over the place in all sorts of domains, from mathematics to music to, of course, social representation. So I believe that this is a very old aspect of human evolution, perhaps prior even to social collaboration and communication. The person who made such a biface probably had a sort of formula in mind that says there were two lines of equal length touching a circle, and artifacts such as these can be as old as 1.8 to 2 million years old. So very old story of hominization. So there is also an aspect to what I'd like to defend is the idea that even when you perceive, you compress information using this language. So perception is sufficient to trigger this compression into minimal abstract symbolic structure, and complexity is determined by minimal description length in this language of thought. And as I said, maybe it's quite old. Maybe it first emerged as a mental representation device. This would make sense because suddenly this is the beginning of science. You can make sense of the world in terms of symbolic structures before perhaps having the ability to communicate it through spoken language. So here is the kind of experiments I will show you. Extraordinarily simple experiment where we look at spatial memory, for instance, here, and we find that to account for these experiments, you need a language. So here's an experiment we run with preschoolers. That's why it's a bit simple in the description here. You have 8 ponds that are arranged in a circle or octagon, and there's a fish that will appear, and your task is to guess where it's going to go next, okay? So we try that. Oops. Well, I was meant to stop it, so I guess I gave you the solution. But did you get the feeling that you knew beforehand that it would go here and then here and then here, right? It's creating this zigzag pattern, which you immediately interpreted. In fact, you would be surprised if the ending was not as you expected. And yet, notice this is even more than single trial learning. It's 1/2 trial learning, something like that, right? Because you started to know the answer before the whole sequence was even presented. So I would love to see a network that is able to do these sort of things, but we don't have one for the moment. What happens here? Well, we think that there is a sort of formula in the head of the viewer that captures the zigzag phenomena. And it says something like this. There is a horizontal movement, and you repeat it 4 times, starting with a different point. Okay? And so the key properties of the postulated language, first of all, are numerical and geometrical primitives, such as rotation around this circle, or symmetries, horizontal, vertical, diagonal, for the particular one I showed you here. And then there is a single recursive rule, which is repetition. You can repeat these operations. For instance, you apply this horizontal operation here 4 times, and you can repeat with variation. I would like to argue that for mathematical structures such as this one, elementary mathematical structures, repetition with variation is essentially what we mean by symmetry. Something repeats with a variation, and that is the key to mathematical understanding. So the zigzag is repeat 4 times, the repeat 2 times, symmetry. Okay, and you change the starting point. So we have quite a bit of experimental evidence that subjects have this in mind. Here's an experiment where each dot is a different sequence of 8 locations. So if it was just working memory, you'd think it's just a number that counts and it's 8. It should saturate working memory. It does saturate working memory when the sequence has 0 regularity, so it has very high minimal description lengths. But as soon as you can compress the sequence and get to a shorter description, then subjects begin to be able to memorize it and to predict what comes next. And this is true also of preschoolers or people who are not educated. They don't recurse as much, perhaps, so there are these 2 points that are a bit off the curve, but they can compress regularities, and of course they have not been educated, so it's not really a matter of education. It's really, I would claim, something that we can all apply to such simple sequences. So in humans, spatial sequences are not driven just by length, they are driven by compressibility. One thing we can do is we can do eye tracking experiments. We don't even have to ask subjects to predict the next item. We can just do that implicitly. We ask them to just follow with their gaze the location of the dot or the fish. But they don't just follow, they anticipate. So what you see here is an index of anticipation for different sequences. In gray is the most complex sequence. You can see there is very little anticipation, even after it repeats. After 8, it repeats, and in fact three times here. So very difficult to memorize a random sequence of 8, but if there is a regularity, like +1 +1 +1 is going around the circle, or alternating 2 operations, or 1 arc on one side, 1 arc on the other, here is the zigzag, which we call 4 segments here. You can see that the eye anticipates, and in fact the anticipations betray the structure. So you can directly see the structure by the amount of anticipation at a different time. So for instance, you see the crosses or the squares here. 2 squares drawn on the screen create this pattern of 2 anticipations growing as a function of being along the square. So once we had this behavior, we could take it, of course, to functional MRI. Maybe I'll try to hide this. Here we go. And so in functional MRI, the prediction would be that there should be a network that's driven by this complexity. It should be more active for the sequences that are more difficult, and difficulty should be driven by complexity, which is minimal description length, or sometimes called abusively a little bit Kolmogorov complexity. So this is what we found, that there's a whole network of areas that covary with this measure of complexity, this compressibility. And if we remove areas that could be accounted for by the distance of the saccades or by the memory demands, we are still left with areas that are really uniquely driven by complexity, in particular in the sort of dorsal part of the inferior frontal gyrus going into the precentral region, dorsal area 44, something like that. It's not really Broca's area, it's just dorsal to Broca's area. But there's a whole network, and we can get an even better correlation if we actually take into account what the subjects do, which is not a linear curve, but actually they saturate and then they fall back for the sequences that they cannot understand, especially the more complex ones. So if we take this pattern into account from the behavior onto the imaging, then we find this very dorsal network, which involves the parietal cortex and the dorsolateral prefrontal cortex, okay, bilateral. And I would like to emphasize that this network is not something that's novel to us. It's the same network that we find whenever we probe mathematical calculations, or at least there is a lot of overlap here. So if we simply ask subjects to do simple calculations, we find that there is overlap with this complexity in the language of geometry. The overlap is shown in green, especially in the right hemisphere, both intraparietal sulcus and dorsal prefrontal, middle prefrontal gyrus. There is no overlap whatsoever with language areas. So it is a language. There is a need for recursion, but it's not the same language as natural language, and it's not occurring in the same areas here. So all of these areas tend to be, in fact, deactivated whenever we do geometry or mathematics. We can also try to track these representations with magnetoencephalography. The point here is that we can follow them through time, unlike MRI. And so here's one thing we can do. We can decode the spatial location where the fish appears. This is actually quite easy because there are many retinotopic maps in the brain, so we essentially track the retinotopy of the stimulated location. You can see that for each of the 8 successive fish appearances, you get a decodability of the corresponding location, and the decoder here as a function of time peaks around 150 or something, but lasts for a long time. So there are multiple areas that are being contacted here. Using this decoder, we can really decode each and every one of the sequences. So if the sequence rotates around the circle, our decoding rotates around the circle. If the sequence, let's say, zigzags, so this is our 4 segments, you can see the zigzagging in the stimulus, you can see the zigzagging in the decoder here. This is all decoding after the stimulus is appeared, but in fact, if you look carefully as a function of time, you find that we can decode even before the stimulus appears. And now it gets more interesting because it means that the subject anticipates with the eyes, but here they don't move the eyes, just with the brain. They are brain signals that anticipate on the forthcoming location. So we get better decodability of the real next point than of a control next point, which is at the same distance from the preceding one. So there are no artifacts of the preceding one. So this anticipation signal is actually, oh, this should appear here. Well, it's not shown on the slide, but this anticipation signal, Fosca al-Rumi, who did this work, showed that it is proportional to the complexity of the sequence. In other words, it appears only for the simple enough sequences. It disappears. It's a negative correlation. Disappears when the sequence is too complex and subjects cannot anticipate. So it is the first indirect trace in the brain that the brain is actually using this complexity measure. It's using this compression, linguistic compression. We can do a little bit more. First, the model predicts that there should be geometrical primitives in the brain. So we should be able to tell not just the location of the items, but actually the nature of the transition. And in particular, there are 11 possible types of transitions, +1, +2, and so on and so forth, or symmetries, as I showed you. So if we train a decoder from the imagery signals to tell what sort of transformation it is, we get excellent decoding, well, excellent, above chance decoding after the moment or around the moment where the transformation is being applied. So in other words, the subject's brain does not stick to location. It actually encodes the transitions as rotations and symmetries. And in this very clean analysis, what Fosca did was to take exactly the same physical transitions. So we move from this point to this point, for instance. But sometimes they are encoded internally as rotations, because in this context, it's just a point rotating. But in the context of the zigzag, they would be interpreted as a symmetry. So the very same transition can be one or the other, and we found that we were able to create a decoder that decodes what the subject sees in this transition, not just what he thinks about the transition, not just the physical stimulus itself, the interpretation by the brain as a rotation or a symmetry. But I wish I could tell you that we decoded the full syntax, because then we would sort of know how the brain encodes it. We could not quite do that, but there is one more thing that we can do here, which I think points to the solidity of this idea of a language. These are just sequences of 8 items, and they repeat. But according to our language, they should be parsed into groups. Okay, so the zigzag should be groups of 2. 1, 2. I go back to a new starting point, and I redo 1, 2, and so on. And there are other sequences, like these 2 arcs here. You do one arc of 4 and another arc of 4. It should be parsed by groups of 4. And there should be a sort of counter. Of course, the idea is that there is sort of programming language in the brain of the subject. So there should be a sort of counter that says, I'm doing the first one, and now I'm doing the second, now I'm doing the third, I'm doing the fourth. Oh, that will change, and I have to go back to the new arc. Okay. Same thing for 2 squares, where you draw a first square and then you draw a second square. So if this view is true, there should be decodability of a token in the subject's brain that says what is the number of the sequence, even though if it is irregular, there is no particular number at all, right? These numbers are self-imposed by the language that the subject is imposing onto the sequence. So I would not be telling you this if we did not manage actually to decode the number that the subject is attributing to these locations, completely orthogonal to the location, because all of these sequences rotate and adopt all of the possible symmetries and so on. But we can decode that the first element appears, and so about 300, 400 milliseconds afterwards, we see a peak of decoding of 1, then we decode the second, and we redecode 1, we decode second, and so on. This generates peaks in the power spectrum at just the proper frequency, which is half of the frequency of the initial stimulus in the case of sequences with groups of 2, and 1/4 of the original frequency of stimulation in case of groups of 4, right? So I think this is proof enough that the brain is not sticking with just the sequence, the linear sequence, but it's going beyond linear and creating groupings that reflect the inner structure that we postulated from behavior. Now, sequence learning is an ideal paradigm to compare humans and monkeys, and we're starting to do that in collaboration with this wonderful person, Liping Wang, who is now in Shanghai in the Institute of Neuroscience. Liping has been able to show that monkeys can learn some spatial sequences. They cannot learn sequences of 8 like we are doing with humans, so this is already way too hard for them, but they can do things like this. So here you see a sample, like 3 successive locations, and the monkey can do the same sequence either repeated or in mirror image. Okay, so the monkey has a working memory of the original sequence. You can see that it changes on every trial, even the length of 4 here, and the monkey will reproduce very fast, actually, the sequence either in forward order or in mirror order. So this is quite an achievement, and it shows that the monkeys do have working memory for spatial sequences, but do they compress them? Or they can generalize this task to new arrangements and so on. So they really have the ability to store 1, 2, 3, 4 locations in their memory and put them out either in forward order or in reversed order. We could discuss what this means in terms of grammar, but several things. First of all, the learning is enormously slower than in humans. It takes thousands of trials before they understand what we want them to do, whereas a child can do it in just a few trials. And monkeys never grasp the geometrical structures. This is from a paper which is still submitted. What Liping and his team did was to study all of the possible sequences on an hexagon. So there are lots of them, but we immediately group them. For instance, a sequence of 4, these are all sequences that involve a movement by 1. On the initial hexagon here. These are sequences that are the same shape. The first 3 are 1, and then there's a jump to another one, and so on. So you get the idea that there are patterns, and they can be rotated in all sorts of ways. Well, monkeys don't care at all about the patterns. So in fact, they have a lot of variance in their behavior across all of the variants of the same pattern, whereas humans behave very, very similarly within a given pattern. And conversely, human adults and children vary a lot in their behavior according to the pattern. And in fact, if we sort the patterns by their simplicity, so this is where the adults are best, and this is where the adults have the most problem with, sequences that cross and so on. Well, you can see that both adults and children have regularity. They care about the transitions, but monkeys don't care at all about the transitions. They just store the locations. So it looks as if the monkeys have a sort of slot-based working memory, as was always discussed in the classical field of working memory. We have something different. We care about the transitions, and if we can compress them, it gets easier to memorize a sequence. Now, in recent work, Samuel Planton in the lab was able to show that this generalizes to auditory sequences, and in fact, very much the same exact language applies. So I will not have time to explain all of the details, but just make you listen a few sequences. They're all 16 items long. So imagine trying to memorize a 16-item sequence, okay? But let's try this. Could you repeat it? I guess you could. And the behavior shows that you could. Let's try a slightly more complex one. I think this one. Got it? Maybe with a second repetition it'll be better. But by and large, you know the structure. Now compare that with a random, which is not really random, but high complexity sequence like this one. Here, purportedly, there are no regularities, and you cannot memorize it. Okay, so we find very much the same thing. These are the sequences. They're all binary sequences now, so it's like the octagon, but there are only two locations, A and B. There are two nodes, A and B, okay? So the language becomes very simple, but it's still the same language. You can compress these sequences by repetitions of repetitions of repetitions with a certain number, okay? And so we present that to the subjects, and we can do several things. First of all, we can just ask them what's the subjective complexity. I guess you could have done that. And it's very clear that subjective complexity is proportional or is related monotonically to the minimal description length in our language, but also objective complexity. So now, after an habituation period, we change just one sound. This is our test of memory. So we change one of the sounds, and we ask the subjects, can they detect it? Do they click a button to detect it? You see that the detection, and this is a mixture of reaction time and errors, but we get it in both, this detection is essentially possible for simple enough sequences that can be compressed, and less possible and slower for sequences that are high complexity. And the correlation is really very, very good here. We even get it for completely out of range sounds, sound C, which you never heard in the habituation, but even then, the compressibility means that you are more concentrated, you are freer in a sense to detect these sounds, and so you are faster as well. So once again, but I insist it's the same language, so I don't think this is a modality-specific language. It crosses from vision to audition. It's just a notion of repetition with certain numbers that suffices, if you apply it recursively, to account for the complexity of the task here. So in the last part of my presentation, I would just like to discuss its application to geometrical patterns. All over the world, people from all sorts of cultures have made spirals or circles or squares. This is in Lascaux. Lascaux includes these beautiful drawings, which are also symbolic. They are not quite like the animal, but they also include things like this rectangle or square or lines of dots. And of course, a circle of stones like this is very nice, but people never saw the circle. It's only because we have a drone that now we can see it's a nice circle, right? People never saw the circle, but they were able to conceive it and build it over years. So, can we understand that? Well, I think it's very much the same story, and with Matthias Sablemeyer, who is here, we designed a language that can explain our sense of regularity in these patterns. So, the language has very few primitives. There is one for number. We can, in fact, resort to just one and the notion of successor, like piano arithmetic. Then we have something like a logo language, which are geometrical primitives. You can move a certain vector, you can turn to the left, and you can trace your path. And the trace is a sophisticated function because it allows you to integrate. So unlike logo, it allows you to draw a circle by tracing while turning by a certain angle. Okay. So this idea of a continuous tracing. Philosophically, I think it's important. These are integers, these are discrete, but these are continuous. And we claim that the human brain has a sense of the continuum, has a pure sense of the continuum. That's why we like spirals and circles. But then the important part is done by these control structures, which allow you to repeat a certain number of times, to concatenate subprograms, and even to have subprograms. Okay. So if we look at a square, we can draw a square by saying repeat 4 times the concatenation of tracing and turning 90 degrees. Okay. And that's one of the simplest possible formulas in the language. But with just one addition, we could do a square of circles. Because of this recursive property, we could call a program that draws a circle, and if we just add it in here, we'll have a square of circles. So the prediction is that we should be able to understand these things based on the language of thought. So we are starting to do several tests of this. I'm afraid I don't quite have time to explain all of it, but first of all, we can generate all of the shapes at a certain level of complexity. So complexity 1 is just a line, complexity 2 is just a circle. At complexity 3, we begin to get a spiral and dotted line, or concatenation of a circle and a line. And you can see that we have a hierarchy of shapes of increasing complexity. It's more complex now than the octagon story, but we can test this. So how do we test this? We present subjects with a single shape. We ask them to press the bar and release it when they are ready, when they think they have memorized what the shape is. So we get an encoding time. And then there is a delay, and they have to choose the shape among 6 possible choices, which are chosen cleverly so that they are close enough to the original shapes in terms of a neural network that simulates the ventral visual pathway. I'll return to that in a second. So what we find is that the reaction times of the subjects, both for the encoding and for the multiple choice, are directly related to the cost, that is to say the length of the program, the minimal description length. And there is another prediction which I think is more interesting, because the one I just showed you is particular to the language. In order to compute this program cost, we have to have a specific set of instructions. And so, in a certain sense, this is a proof that we have a set of instructions which is close to the human one. But we can also test a generic prediction. The generic prediction is that whenever you create a program with the instruction to concatenate, to repeat, or to embed, there should be these additive rules. For instance, if I repeat a certain program, I should have the complexity of the original program, which is just a constant, which is the cost of adding the instruction repeat. And the same for concatenating and embedding. Embedding is particularly interesting because it means, it's the notion of sub-program, right? It means that you can do a square of circles, and you could do a square of circles of squares with extremely minimal cost, which is just the additional cost of each of the program and a certain constant. So I will not go into the details of all of that, but we selected shapes like this, and then we created circles of squares and all of these shapes, and we showed that these equations, using the same exact method as before, that these equations account for the reaction times of the subjects. The reaction times of the subjects show that these sort of equations apply, and in fact, these shapes are not complex. They look complex, but they are just a simple sum of the complexity of the inner shape and the complexity of the outer shape and some additional constant for the embedding. So I think this is some of the strongest evidence that regardless of the specifics of the language that we are proposing, there is also something true about the notion of a recursive ability underlying the ability to perceive shapes. I'd finish with an experiment that was just published, a series of experiments that was performed by Matthias Sable-Meyer on the perception of quadrilaterals, which is the simplest possible thing we could think of, you know. So here is your task. You just have to spot the oddball. Okay, did you spot the oddball? I guess it's not too difficult here. Okay. So we did this with all sorts of shapes, with the idea that some were simple, like rectangle or square, because they are compressible, they have a lot of regularities. And as we move down here, they are less and less compressible until we get to this completely irregular quadrilateral with no particular regularity. So in all of these cases, we take the bottom right point, we move it by a fixed amount. So this is important. It's the same exact amount of movement, displacement, and we ask the subjects to detect the oddball that was created by one of these 4 possible movements of one of the dots. Okay? So if it's just physical displacement, should not be more difficult to do it with this shape than with this shape. But what we find is a beautiful regularity effect. It's much, much simpler. These are error rates now. If I displace a point on this irregular shape, you might make as many as 45% errors here. It's very hard to detect the oddball, but it becomes super easy when the shapes are regular, because you notice the regularity and you notice the violation. So we found that this is an extremely universal effect. All humans seem to show this. So we went again to test preschoolers in France, also in collaboration with Serge Caparros. He went to test the Himba in Namibia, people who have very little or no education, formal education, but they still show this regularity effect. We also did, I will come back to the deviations here in a second, but we also tested the abstraction, for instance, by testing a sequence format. You don't have to see the shape. We can just show you the four corners, one after the other, and this is enough to evoke the corresponding program. So I think it bridges with the previous task. Whether it's a sequence or whether it's a shape, static shape, you can compress it using very, very similar complexity. The question, of course, is it unique to humans? And we are lucky enough to collaborate with Joël Fagot, whose name was already mentioned in this conference, to test this in baboons. You know that Joël is running this incredible facility where there is more than 30 baboons, and they can at any time enter this booth, 24 hours, so some go in at 2 in the morning, and they will find a computer that recognizes them and presents the next trial of some experiment. So we typically get thousands of trials, 1,000 per day typically. We get wonderful data, and we can train baboons. So we started by training them on this oddball task, because they have to understand what they have to do, right? So we trained them with non-geometric shapes, such as these flowers. They have to pick the oddball. And in fact, they had to pick the oddball of each of these vertical pairs here. So let's say the blue amongst red or red amongst blue. Once they knew how to do these oddballs, we generalized to these shapes down here. So we really were sure that they knew the task. They knew the task, find the oddball. But then we transfer them to the geometric shapes for the first time, and there is no geometrical regularity effect whatsoever. In fact, they find the task very difficult, so they start above chance, but close to 75% errors. Chance would be 86, because it's 1 out of 6 correct. So you see that there is essentially flat line here. They do get better, but they get better with thousands of trials once again. So they really don't understand, and they don't get better for the simpler shapes before they get better for the more complex shapes. So they still have no regularity effect. The correlation is non-significant here. However, they do something. The baboons do something. So these are all of the baboons, and they all get highly correlated with each other across the shapes. So they all have the same sort of response profile. They do something with these shapes. It's just not the same as what humans do. So in order to understand what they did, Matthias developed 2 models. One is a symbolic model that I already described to you. I simplify, of course, but we just count the internal properties, how many right angles, how many parallel lines, how many equal lines, and so on. And the list is a code for the shape, and then we can detect the oddball by the function of how distant it is from this shape. Okay, so that's the symbolic model, and it accounts well for what happens in the humans. So as the shape becomes more complex, it has fewer properties, it begins to be harder to detect. But we also developed this convolutional neuronal network. In fact, we tested a lot. That is supposed to be a good model of vision in humans. It's a good model of the visual pathway. Was selected. We used the cornet network in this particular figure. The cornet is supposed to be a good model of V1, V2, V4, IT. It's been found to fit well in the monkey. And so what we did, we fed each of the 6 images here. We computed the vectors at each stage. And at each stage, we could ask, well, which vector is more different from the mean of the others? Which vector is different from the others? Okay, so that was the way to compute how this network would respond to the oddball task. And what you see now is a complete separation. You also see this in this matrix form. All of the baboons go with the neural network. All of the humans go with the symbolic model. This is what you see in these columns here in this multiple regression, right? So all of these on the right, although they have funny names, they're all baboons. They are all modeled by the convolutional neural network. But the humans require the symbolic model. Now, interestingly, the Himba and the preschoolers, they are in between. They are fit by a mixture of the 2 regressors. We think that this means that there are actually 2 strategies. As humans, we are still primates. We still have a ventral visual pathway, and we can use it to detect the oddball. But we can also use this additional symbolic model. And it's a mixture of strategies that account for what happens in preschoolers and HIMBAS. But even the preschoolers already have a significant contribution of the symbolic model. Voilà, so I've reached my conclusions. I think this is the best evidence so far that we have that humans are quite special. And we are trying to compare with chimpanzees now, but at least with respect to baboons, they are quite different. Something different from the ventral visual pathway is appearing and is necessary in order to account for all of these tasks that I've been showing you. And so my conclusions is that humans, unlike other non-human primates, possess mental programs in a language of thought. The language discretizes. It uses discrete symbols, and it performs one-shot learning on such symbols and their combinations. It's able to infer program, and in fact, according to this view, shape perception, at least for geometrical shape, is program induction. And we can connect that to the program induction that Josh Tenenbaum, for instance, has been developing. We are working together to model this data. All humans consider the same programs as simple, regardless of their culture. So that could explain why there is so much cross-cultural convergence in math. This is, of course, an extreme example of the Pascal triangle in China. So many mathematical concepts have been discovered multiple times, and I think squares and rectangles are among the most obvious, or circles and spirals, because we have the same language of thought. But there is also a consequence for AI of what I've been showing you. We still don't have very good models of symbolic learning. I think it escapes a lot of what we've seen today, but that's for discussion. But I'd like to stress that this is true even for the perception of a square. The perception of a square is not captured, for the moment at least, by AlexNet, by CoreNet, by all of these networks that are supposed to be good models of the ventral visual pathway. We are starting to do fMRI now of these tasks, and indeed we're finding that it's not in the ventral visual pathway, but much more in the parietal cortex that these shapes tend to be perceived. So I think something quite different is happening, which is in fact the beginning of mathematics in these tasks. With that, I will close, leave you with this little joke from the New Yorker and the face of Matthias, who did most of this work. Thank you very much.